Have you ever looked up at the sun, that brilliant, life-giving orb in our sky, and asked a simple yet profound question? Where did it all come from? How did this magnificent star and our entire planetary family spring into existence? It's a question that connects us directly to the grandest story of all, the story of cosmic creation. Long before there was an Earth to stand on, before there were any planets at all, this corner of the universe was dark and empty. There was no sun to warm the void. There was just a vast, cold, and seemingly unremarkable cloud of gas and dust, drifting silently through the immense blackness of interstellar space. This cloud, which astronomers call a molecular cloud or a nebula, was truly enormous, stretching for light years across. It was a ghostly mixture of the most basic elements in the universe, primarily hydrogen and a little bit of helium, left over from the Big Bang itself. But it was also seasoned with a fine sprinkling of heavier elements: carbon, oxygen, iron, silicon. These heavier elements were forged in the fiery hearts of ancient, long-dead stars that had lived and perished long before our sun was even a thought. As this immense cloud began to collapse, of gas, of dust, something truly elegant started to happen. It began to spin. Just like an ice skater pulling their arms in, the spin sped up as it contracted. Conservation of angular momentum, a fundamental law of physics. Any slight, random rotation at the start became dramatically amplified as the cloud shrank. That spinning motion helped shape our solar system. Material couldn't just fall straight to the center. Centrifugal force resisted gravity's inward pull, strongest along the equator of the rotating mass. Think of spinning pizza dough. It flattens into a wide, thin disk. The same thing happened to our cosmic cloud. A lumpy sphere morphed into a flattened, rotating structure, a protoplanetary disk. At its center, a dense, hot ball of gas was forming, the embryo of our future sun. The new disk was bustling and chaotic, a cosmic whirlpool of gas, dust, orbiting the glowing protostar. Temperatures varied dramatically across the disk, scorching near the center, frigid in the outer fringes where exotic ices formed. All eyes, if there had been any to see, would have been on the center of that spinning disk. Here, at the core of the collapsing cloud, the pressure and density were becoming unimaginable. Gravity was relentlessly squeezing the material, primarily hydrogen gas. As the pressure skyrocketed, so did the temperature. The core of this nascent star grew from thousands to millions of degrees Celsius. It was a pressure cooker of cosmic proportions, building toward a moment of spectacular transformation. The heart of the cloud was becoming a furnace. For a long time, this central object was simply a very hot, very dense ball of gas, glowing with a dull red light from the sheer heat of its compression. But it wasn't a true star yet. A star is defined by what happens in its core. To become a star, it has to unlock the most powerful energy source in the universe. The conditions in the core were approaching the breaking point. Hydrogen atoms were stripped of their electrons, forming a superheated plasma. The stage was set for the ultimate act of creation. Then it happened. When the temperature in the core reached about 15 million degrees Celsius, a threshold was crossed. Hydrogen nuclei, which normally repel each other, were forced to slam together and merge. This process is called nuclear fusion. In this cosmic alchemy, hydrogen fused to create helium, releasing a tiny amount of mass as a tremendous burst of energy. Light flooded out from the core. Heat flooded out from the core. In that instant, our sun ignited. A new star was born. Fusion's outward push met gravity's inward pull, creating a stable balance that has let our sun shine for 4.6 billion years. At the same time, the young sun unleashed a ferocious solar wind, sweeping through the protoplanetary disk like a powerful broom, forever changing the environment in which the planets were forming. While the sun was igniting at the center, the rest of the disk was far from quiet. It was a cosmic construction yard where worlds were being built from the ground up. The process began with the tiniest of particles, microscopic grains of dust, microscopic grains of ice. These grains, swirling around the young sun, would gently bump into each other. Thanks to electrostatic forces, these tiny grains began to stick together, like how a balloon sticks to a wall after you rub it on your hair. A grain stuck to another grain, then another, slowly growing into cosmic pebbles. This process, known as accretion, continued relentlessly. Pebbles collided to form rocks. Rocks crashed together to form boulders. Over millions of years, these collections of rock and ice grew larger and larger, eventually forming objects hundreds of kilometers across. We call these bodies planetesimals, literally tiny planets. The solar system was filled with countless planetesimals on paths that often crossed, leading to an era of constant spectacular collisions. The biggest planetesimals had a distinct advantage: their gravity. Once massive enough, they pulled in smaller objects and grew even faster in a runaway effect. The rich get richer, even in space. In the inner solar system, only materials with high melting points could survive. Rock, metal, Mercury, small, dense, and rocky. Venus, small, dense, and rocky. Earth, small, dense, and rocky. Mars, small, dense, and rocky. Worlds built from refractory materials. Further out, beyond the frost line, it was cold enough for water, ammonia, and methane to freeze, making much more solid material available to build planets. Giant cores of rock and ice became massive enough to capture vast amounts of hydrogen and helium. Jupiter, Saturn, Uranus, Neptune, majestic gas giants unlike their rocky siblings. So let's recap this incredible journey. It all began with a vast, cold cloud of gas and dust. A cosmic nudge caused it to collapse under its own gravity. As it collapsed, it began to spin, flattening into a protoplanetary disk. In the super-dense, super-hot center of this disk, nuclear fusion ignited and our sun blazed into life. Meanwhile, tiny dust grains stuck together to form pebbles, then rocks, and eventually planetesimals. These building blocks collided and merged, with the largest sweeping up the others to become the planets we see today. It's a story of gravity, motion, and time. It explains why the rocky planets are near the sun, the gas giants far away, and why all the planets orbit in the same direction on nearly the same flat plane, the legacy of that initial spinning disk. Events like the formation of our moon, likely from a giant impact with a young Earth, were part of a violent solar system settling down. The universe is not just stranger than we imagine, it is stranger than we can imagine. The iron in your blood, the calcium in your bones, the oxygen you breathe. Every one of those heavier atoms was forged inside a star that lived and died before our sun was born. That star exploded, scattering its creations across the galaxy. Those elements became part of that great molecular cloud, which formed our sun, our planet, and ultimately, us. We are, in the most literal sense, stardust. We are the universe's way of knowing itself.